In this lecture, we'll look at Gauss's law, but before we can do that, we should review a few things. So let's start by looking at how the electric field is affected by different charge distributions. Starting with the simplest one, a point charge, and we know that a point charge can be positive or negative. So for a positive point charge, we know that the electric field lines radiate radially outward, and this should be a three-dimensional drawing where we know that the electric field lines are spherically outward of the positive charge. For a negative charge, we have the electric field lines going radially inward towards the charge. Now the equation is the same for the magnitude of the electric field. So that is the absolute value or the magnitude of the electric field is equal to the electrostatic constant K times the magnitude of the charge divided by the distance from the charge squared. So this is just the magnitude. The direction is given by away from the positive towards the negative. Now if we use a positive and a negative charge that are have the same magnitude and they are very close together, we form something called a dipole. So here I have a positive charge and a negative charge. They have the same magnitudes, and we know that electric fields go away from positive towards negative, but then what we used to have as a straight line over here bends and goes towards the negative. So the electric field lines will bend like that, and then we still have the ones in here that are fairly straight, but there is this behavior when we put two charges close to one another. Then if we know that the magnitude of the charges are q, so we have a plus q and a minus q here, separated by a distance d, then an important quantity is a dipole moment, and the symbol for that is p, and in absolute value the dipole moment between two charges is given by the magnitude of one charge times the separation between the charges. The direction of the dipole moment is in the opposite direction of the electric field. So it points from the negative charge to the positive charge. The electric field is proportional to this dipole moment. Now another configuration is the parallel plate capacitor. So here we have a positive plate facing a negative plate. So they're parallel plates and they store charges on these plates. There is a separation here. There is nothing in between the two charges, so that we can't have electrons hopping across. They don't move from one side to the other of the capacitor. But we know that electric field lines go away from positive and towards negative, so they will have this shape between the parallel plates of the capacitor, and something we're disregarding are edge effects. So there would be electric field lines curving out like this at the edges, but we're not going to look at those. So we'll just pretend that the electric field is going to be parallel lines like this here. Now the electric field between the parallel plates of the capacitor is given by sigma over epsilon naught. Sigma is called surface charge density, so it is the charge on one plate divided by the area of one plate. So then the magnitude of the electric field is Q over A, charge over the area of one plate divided by epsilon naught, and the epsilon naught is 8.854 times 10 to the negative 12 coulomb squared per Newton meter squared, and it's called the permittivity of free space. The permittivity of free space is related to the electrostatic constant by this equation. So we have K is 1 over 4 pi epsilon naught. Now another very important thing to know about the electric field between parallel plates of a capacitor is that no matter where exactly, what point you are looking for the electric field, it has the same magnitude. So anywhere in this area between the parallel plates, the electric field has this value. So we've seen now that depending on what type of charge distribution we have, point charge dipole or a parallel plate capacitor, for instance, the electric field is a little bit different. It has different magnitudes, and then we need to be able to get a more general equation, more general method of figuring out the electric field due to various charge distributions. So to do that, we first have to discuss electric flux. So the electric flux, stated simply, is the electric field lines that are crossing an area. So here we have an example of an electric field. So we have electric field going this way, and then we're placing an area here that we're trying to see how much electric field crosses that area, and that would be our electric flux. Now, an important thing for this area is the area vector. So the area vector is perpendicular to the geometrical area, and it points out from the area. So it has the magnitude of the actual area. In this case, it would be a pi r squared for a circle. But it also has a direction, and we have to remember that the direction is out of that area. So if I orient my electric field so that it's parallel to this area, then all of the electric fields go through. Had I had electric field lines going in this direction, then some part of the components of the electric field would have gotten through, but not all of them. So we would have lost, as it were, some of the electric fields passing through. So the important part is that the electric fields that have a direction, an orientation that is parallel to the area vector are going to pass through this area. So then the electric flux is given by the dot product between the electric field and the area vector, which translates to the magnitude of the electric field times the magnitude of the area times cosine of the angle between them. So in this case, the angle between the electric field and the area is 0, so cosine of 0 is 1. As I said earlier, if we had an electric field that goes in this direction, then we would have had to take the angle between the electric field and the area vector, and then only the components of the electric field that were parallel to the area vector would have made it through. So now, how can we find the electric field due to any random distribution of charge? The answer is, of course, Gauss's law. And the equation for Gauss's law is this. I know it looks intimidating, but we will work through it. So it's the sum of the electric field lines dotted into an area dA is equal to the enclosed charge divided by epsilon naught. This equation is actually the equation we saw earlier for the electric flux. So what do we do with this? So let's say that we have a point charge, and we know that a point charge creates electric field that is radially outward. So here is the electric field. And then let's say that we want to find the electric field at a point r away from the charge. But where exactly is this point r? Is it here, or is it there, or is it here or there? There is an entire sphere that is a distance r away from the point charge. So then we're going to draw this imaginary surface here, and we will call it a Gaussian surface. And we know that along this surface there will be the same electric field because it's at the same distance r from the charge. So this Gaussian surface will help us remember that we are going to sum over all of the electric fields that cross small little areas along this Gaussian surface. So I'm just going to look at this particular electric field line here, and that pierces a tiny area that we call dA. Now this area dA has an area vector, dA vector symbol, and I know that the electric field and dA are along the same line, which means that the cosine of the angle between them is going to be 1 because the angle between them is 0. So our E dot dA becomes just E dA. So Gauss's law then translates to the sum of E, magnitude of the electric field, times the magnitude of the area vector times cosine of the angle between them is equal to the charge enclosed by the Gaussian surface divided by epsilon naught. So if we sum over all of these electric fields piercing tiny little areas, so here where we have the electric lines already drawn, it's easier to visualize, but this is here as well, and remember that this is a three-dimensional model. Then if we add over all of the electric fields that pierce through this the area vector, we end up with the electric field times the entire surface of the sphere. So the left side of the equation becomes electric field times 4 pi r squared, the area of a sphere, and then the right side of the equation is the charge enclosed by the Gaussian surface. So this is the Gaussian surface that we picked, and the charge that's enclosed by it is basically the Q that's in the middle here. And then we have Q divided by epsilon naught. So then the electric field becomes Q divided by 4 pi epsilon naught r squared, but K is 1 over 4 pi epsilon naught, so that means that the electric field is KQ over r squared. And this is something that we know. We knew already that the electric field due to a point charge was KQ over r squared, but now we use Gauss's law to show the same thing. Now, let's look at shielding. What is that? So let's compare a conductor with an insulator. Let's say that we have a conducting sphere and an insulating sphere, and they are neutral from an electric point of view, and then we bring a rod that has charges on it and touch the conductor, and then we bring a different rod and touch the insulator, and what happens is this. On the conductor, since charges are free to move about, they will like to be as far away as possible from one another because there are electrostatic forces acting on all these particles. So they will distribute themselves so that they are as far away from one another as possible. For the insulator, since charges are not free to move around, when we place charges somewhere in the insulator, they will just basically stay wherever we put them. Now, in some insulators, you can distribute charges fairly uniformly, but they are all throughout the volume of the insulator. With a conductor, the charges arrange themselves on the outside. With the insulator, they just go anywhere. Then, if we draw a Gaussian surface inside the conductor and inside the insulator, what we notice is that from Gauss's law, the charge enclosed is 0. So when we look at Gauss's law, we notice that the right side of the equation, the Q enclosed by the Gaussian surface here, we have no charges, so it's 0. Whereas for an insulator, we have the charges enclosed are not equal to 0 because there are charges throughout this insulator. So then we mean to say that there is a shielding effect in the case of a conductor because all of the charges distribute on the outside and there is no electric field inside the conductor. So the electric field inside of a conductor is 0. The electric field inside of the insulator that has excess charges on it is not 0 because they are not free to move about and distribute themselves on the outside the way it happens with a conductor. So now let's look at a demo. This is a Van de Graaff generator. There is a belt here that once we turn this on will rotate around here. There's some brushes inside this dome, and the brushes will rub against this belt, so it's like scuffing your feet on a carpet. Static electricity builds up and gets distributed on this dome because it's a metal conductor, so the charges will move to the outside, so onto this conductor. Now, To this dome, we have little pieces of paper taped, and we'll see what happens when we turn this on. So here we have the charges built up due to this belt rubbing against those brushes, and we see how the paper strips are going to be repelled by these charges, and since they are tucked down here, they're taped to the dome, they can't really fly off, but they just take this cool shape. And then after we turn this off, once we touch another metal surface to the dome, then the charge leaks through the metal and there is no more charge on here. So let's see this one more time. Electricity builds up, strips are being repelled, we turn this off and then discharge the dome so that the paper falls back down.